Welcome. My name is Barrentine. I am a data scientist. Unlike real scientists, I guess I work mostly with web data that is of little or no consequence to humanity, namely Twitter and Facebook. Sorry if there's any employees of Twitter and Facebook in the audience. And so my talk for today is on Disco, which is a MapReduce implementation. I'll get into that in a minute. But also just on a couple of general themes of using NumPy, SciPy kind of with, or in the context of distributed MapReduce jobs. So that database guy is my Twitter handle. You can follow me or tweet at me or tell me horrible things that I've said that are wrong. I'm sure there'll be at least one. Let's see. So my general interests are, I usually work with text data, so it's going to be, some of the themes I'm going over may be a little bit different than some of the data sets that you guys work on. I do a lot of topic modeling, so latent Dirichlet allocation and friends. And so today we'll go over some of that kind of stuff.
So on your session started, we're running about 5 minutes late.
Oh, cool.
So,
yeah.
Just to announce, welcome out.
Sorry.
Talking about Disco. We're running about 5 minutes late, but that's okay because we have a canceled talk in the afternoon session. So what we'll do is we'll run a little bit into the break, and I apologize for those of you who are going to run upstairs to the talk on the other side. But I'm just going to get out of the way and let you go. And I'm going to give you your full time.
Oh, cool. I thought I was late, so I just kind of started. Okay, cool. So so for those of you just joining us, this is the SciPy Disco talk. I'm Al. I'm a data scientist. That's my Twitter handle. We're going to go over a brief discussion of Disco and a little bit on MapReduce. I'm actually kind of curious, before I start, how many of you have heard of MapReduce before? I hope the whole room, good. How many have used it, written a MapReduce job of some kind? How many of you have written a Disco job? 2, all right. All right, that's awesome. Cool, so let's get started. So Disco, it's a MapReduce implementation without Hadoop. I personally prefer that. Pardon?
Do you want to say a couple of words about MapReduce, the concept?
Yeah, I'm going to go into that in a second, so no worries. Everybody's at least heard of MapReduce. They have a vague idea of kind of what it is. We'll go into that in a minute. Yes, Disco, implementation of MapReduce comes from Nokia Research. It is a Python front end with an Erlang back end. Erlang is the master process, the Disco master process is an Erlang process which handles coordination of your distributed nodes in your cluster, as well as job scheduling and taking care of things like data locality and that kind of stuff. But the actual workers are designed to be written in Python. And empirically, I've found it to be a lot faster than Hadoop streaming when writing your jobs in Python. That doesn't necessarily follow that it's faster than Java Hadoop. But if you're of the same mindset as me, Java is a terrible language for data analysis, and you'd prefer to write your jobs in Python. So, sorry if I've offended anyone with that. My data set is the Twitter fire hose, all of the Twitter fire hose. It's about 600 gigs a day. I keep 30 days or so around in my Disco cluster, and so it amounts to about, I think, 9 or 10 terabytes compressed. I can check that in a minute. So somebody scoffed at that. So I guess, I don't know if that's like child's play kind of, but yeah. I understand. The full data set is much larger than that, but I only really ever care about the recent stuff, and then sometimes there's sort of a cost. This is deployed in EC2, so there's sort of a how many EBS volumes do you want to actually pay for to keep around data where you mostly care about the last hour more than you care about the last 30 days. So yes, we've So Disco allows a lot more flexibility, I think, than Hadoop. There's a lot more pieces of it that are programmable easily from Python. There's a wire protocol. It's not actually. I shouldn't say. There's an HTTP protocol that you can use in any language, and there's a couple that have been written. I've seen one in Java, one in OCaml, and I don't know if I'm even saying that language right. There's the multiple ways to write workers in C, even through the Python API. I'll say a quick word about so a distributed file system underlies any MapReduce setting, and Disco comes with its own, which is pretty cool. So that's what I currently use. You don't have to use the Disco distributed file system. In fact, Disco blobs are just URLs that contain the host name. So you could technically use Mogile FS if you wanted to, or you could use a like Ceph or something like that. Or even HDFS, but you'd have to do a little bit of legwork. I'm thinking about writing some libHDFS stuff for Disco for people who have existing data in HDFS. So yeah, DDFS is built on top of just regular Linux file systems. So you can go to your machines and ls your files and they're real files. I guess that's true of other things too, but it's a tag-based file system, which is kind of interesting. So there are blobs of data which may correspond to your files or chunks of your files. You start with some input files that are usually raw sort of text data. They may be log files. They may be, in the case of the Twitter Firehose, it's just JSON, blobs and blobs and blobs of JSON. And you chunk them into 64 megabyte chunks, which are 128 megabyte chunks, some chunk size, and you store them in the file system. And then multiple tags can reference those blobs, and tags can also reference other tags. What I usually do with Twitter is it's a kind of a hybrid streaming and MapReduce sort of setting. So we take 10 minutes of the Firehose and write that immediately to disk from the stream, chunk it to DDFS, and then tag that with an hourly tag and a daily tag. So you can kind of have 3 levels of granularity at which to run your jobs. There's more things you can do with that. That probably means I'm talking too much. It's never a good sign when your computer goes to sleep. So you can also push. So in a distributed machine learning kind of setting, you can push some global state information. Particularly, I use vocabularies for LDA. It's important that you have kind of your fixed vocabulary stored somewhere. So a lot of times I'll use a tag for that, and then any job can reference it. More information on Disco at discoproject.org. For those of you who haven't heard of MapReduce or are new to MapReduce, I promise I will not use the word count example again, ever. This just happened to be a diagram, and I didn't feel like making my own. So I'm going to come over here and point at things. So this isn't the full picture either. I was trying to kind of munge the Google one that has the actual user program, which is important, and kind of where processes are getting forked and et cetera, but doesn't really matter. So pretend that you have a bunch of these input files. Really, it's not that one line is going to one mapper, it's that one entire chunk is the domain of a single map task. So so yes, this is the data flow of a MapReduce job. So I may have some text files that look like this: dear bear river, car river, dear car bear, and a mapper is a thread, or in the case of Disco, a process which can run a user-defined function. In the case of Disco, it's actually just a Python generator, and it's called over and over again with each line of the file. So this would really be sort of happening in one mapper. If this were a single file, the mapper would get called with this line, again with this line, and again with this line, and then it can emit 0 or more key value pairs. So in this case, it's just counting words. So it's saying all right, split it on white space and emit these keys and values, deer 1, bear 1, river 1. And then there's another stage here called the combiner, which is in any practical setting you really need to write, because you can sort of see that if this were all one map task, that I'd have written this string key and this value to disk n times for the number of times that deer occurred in the document. That'd be really inefficient. So the combiner is a stage where you can aggregate those. So at this point, we're on the local disk of a single map machine, right? So and it has worked deterministically as hard as it could on this little chunk of data, and it doesn't know anything else about the state of the rest of the system. Here's the point during what is often called the shuffle, where you have the opportunity for global communication. So the reason that we have keys and values in MapReduce is that they are hashed, and they're hashed to a particular partition to be used in the reducer. So, in this case, we've hashed, all the times that we saw bear, we hashed it to some value and modded it by, let's say we have 4 reducers here. We've modded it by the number of reducers and assigned it to a partition. So it's written to these partition files on the local disk, and then those files are downloaded downstream by the reducer tasks, which then so basically what that guarantees is that every time I've seen bear, it's going to go to the same reducer. So if I wanted to count the number of words, bear would always appear in this partition and car would always appear in this partition. You don't know specifically which partitions they're going to, but you know that every time you see the same key, it'll go to the same process downstream. The reducer is another user-defined task, which can then, in this case, all it's doing is saying, okay, I'm going to read these key value pairs from my local disk because I've downloaded them from all these map tasks, and then I'm going to just sum the values. And again, the reducer also may output a key and value. So it's going to output deer 2, river 2, etc. That was probably a much lengthier introduction than most people needed. So I decided that I was going to do this talk mostly as a worked example. Hopefully I have enough minutes left to do that. I decided I didn't want to use word count because word count is too simple for most real contexts. So instead I decided to build a job that calculates the PMI, or pointwise mutual information, of words in a document. So it doesn't have to be words in a document. This is used in many scientific domains. I've seen some papers that I don't fully understand the science of, but are using PMI for drought-distressed plants and image data, that kind of stuff. So we're going to do this in a single pass using NumPy. We're going to use NumPy and SciPy.sparse. We technically don't need SciPy.sparse in this one, but whatever. And a few MapReduce tricks, some of which are available only in my fork of Disco at the moment, but I promise they will be available in regular Disco soon. So PMI is log base 2 of the joint probability of x and y over the product of the probability of the marginals. Here we're estimating that probability p of x and y from the co-occurrences of words within a window of 10 words of one another. So this will kind of get words that occurred in the same paragraph versus saying that like every word that occurred in this document is a co-occurrence of every other word, which is not usually reasonable to say. In the case of, so I ran this on Twitter, and in that case I don't really need to care what the window is. It just matters that they occurred in the same tweet, because you can only fit whatever 15 or 20 words into a tweet. Disco for the win. So I'm going to do this section by section and show you the anatomy of a Disco job. This is just the basic setup of a job, a couple of imports of things that you need. Here you're in one Python file, and this will actually be shipped over to all the mappers, and it'll try to do some, especially if you use the subclass of job, which is here, it'll actually try to do some intelligent things with dependencies and shipping libraries over that you need. So yeah, so we're just going to use this simple co-occurrences function to take an iterable, which is the tokens in a document, just use a double-ended queue, append to the right, pop from the left, and get the co-occurrences in a particular window. Mapper, not much going on here, but there's a couple of things to note. Because of the way Disco does sorting or builds the disk-based sort file, these characters are not allowable in the key itself. So we're going to have to just make sure that any token that we're emitting doesn't have those two characters. And then again, we're just using very simple tokenization. In practice, I actually build my code as a Python package and ship it to all of my machines so that I can have some standard tokenization code and that kind of thing. The only interesting thing that we're really doing in this mapper is the prefix. So what we're actually going to do here is, there was one step I neglected to mention, is that in the stage where you shuffle and communicate between the mappers and the reducers, it's not direct communication, but it's, you hash the keys to partitions and they're downloaded by the reducers. There's actually a sort that takes place. So you can guarantee that that the keys that the reducer reads, if you choose to sort it, in the case of Disco, will be read in sorted order. And so what we're actually going to do is for calculating PMI, there are two, remember from the equation, there's two frequencies that we need. We need the frequency of the co-occurrences, and then we need the frequency of the actual words. So in this case, frequency is a little bit fuzzy. It's not the times that the word occurred. It's the number of co-occurrences in which the word occurred. So we have this map method, which is in the master version, Disco has to be a static method. In my fork, it can be a class method or an instance method. We are going to, you can read the rest of the simpler part of the Python. We're going to yield as a generator the words and then the co-occurrences separated by a comma. And next, we are going to go to the combiner. So the combiner, right? We've seen the same word. We've probably seen the word the, 8 million times, or if we use stop words, we eliminate that. We've seen the word I'm in the case of Twitter, many times. The word Twitter, the word follow, things like that. So here, what we're going to do is we're going to use Disco's combiner, which basically every time you've called the map function, the combiner will get called with the keys and values that your mapper emitted, as well as a mutable buffer, which is just a dictionary that you get to store things in memory before you write them out to disk. So you can sort of sum things up here, or you can, I even sometimes do matrix operations or like batch operations in the case of LDA in this combiner when the buffer size has reached a certain amount. So this is all, we're still all in memory here. We haven't written anything to disk. I'm specifying that we want to do a sort equals true means I want to do a disk sort. In the Disco docs, sometimes they'll define a reducer where they actually use Python's built-in sorted, which will actually pull everything into memory, and that's not practical for any data set of any size, of any substantial size. So so yeah, the combiner will generally look like this. This is what's just a general summing combiner. So we're going to say if the key is in the buffer, or if the key's not in the buffer, put a 0 there, append the value, or add the value that I just got from the mapper, and then there's one other piece of this, which is when the block that this map task is reading is done, it will call the combiner again with a null key in value or a none key in value the buffer and done equals true. So you can sort of say if not done, add stuff to the buffer, else yield the keys and values to the buffer, which will then be written, yield the keys and values from the buffer, which will then be written to disk. Disco also lets you define the partition function. This particular piece is only in my fork of Disco at the moment, but so one of the things that Disco lets you do is the basic way that you would route a key to a particular reducer is you would hash the key and mod it by the number of partitions. So it'll call your function. This is something that works on your subclass. 1 minute? Wow, okay. So, right, so the only interesting thing here is we're going to send all the keys with word prefix to all the partitions. That's something in my fork. And then we're going to hash the first word of the key and mod it by the number of partitions to route it to the reducers. Reducer code, I'm not going to have, unfortunately, I'm not going to have enough time to go over in much detail. But this is where things actually get interesting. And so we're going to use NumPy's excellent from iter method, which lets you, which will take any arbitrary generator and you can define the D type, a NumPy D type, so a record. It can be any kind of structured array, or it can be just a regular NumPy type that generator will emit. And so basically what I've done here is I've guaranteed that the words will come to the reducer first because I've sorted by the prefix, because that's the first character in the sort. And then I can sum the marginals in every single reducer so they all get the same list of keys. And then I can, in the second part, read in the, this is a little bit of code that I don't have time to go over. I can read in all the co-occurrence data and then build the marginals as an actual, I'm actually building this as a SciPy sparse coordinate matrix, which is just is storing the data as 3 arrays, one for the row. So it would be, for all the non-zero values in this matrix, you would store the value of the row that's non-zero, the value of the column that's non-zero, and the value of the data that's non-zero at the same index in each of these arrays of the same length. So it's just kind of like an edge list in a graph. And so, yeah, so I'm building that and taking the top 10 values in terms of PMI and yielding them to the output file, which can then be downloaded from Disco. And so these are some of the results that had high PMI. Dwayne Reed, hiker, rescuer, discarded fishnets. I don't know why. You see some interesting use of hashtags that have. So the intuition of PMI is that if 2 words have a higher probability of occurring together than their marginal probability of appearing separately, they'll have higher PMI. So you can see some different kinds of hashtags. Hash Mormon, hash LDS, I guess, are often used together, more often used together than they are apart, and than some of these other ones. I think we're unfortunately done at that point. But I'll post the slides online, and you can take a look at the code in a little more detail.
So I'm using,
Before we start with questions, this
Yeah.
is a quick thing. The speaker. We've got a